Welcome, cosmic explorers. Today, we are embarking on the most incredible, mind-bending journey imaginable. We are going to answer a thrilling question: what would truly happen if you fell into a black hole? Forget the science fiction movies for a moment. The reality is far more strange and wonderful. Our story begins not in the dark center, but at the very edge of this cosmic monster, a boundary known as the event horizon. Imagine you are an astronaut, floating in the silent, black void of space. Ahead of you lies a black hole. From a distance, it looks like a perfect sphere of utter blackness, silhouetted against the glowing gas and stars of the universe. This black sphere is not a solid surface. It is a point in space where the gravity becomes so powerful that nothing, not even light, can escape its pull. The boundary of this sphere is the event horizon. Think of it as the ultimate point of no return. If you cross this line, you are committed. There is no going back, no sending a rescue message, no changing your mind. The gravity beyond this point is simply too strong. As you begin your approach, you are still safe. You are in control of your spacecraft. But the black hole's gravity is already starting to influence you. This is a gentle, persistent tug, like a river current slowly pulling you toward a waterfall. At this stage, everything seems normal. But if you were to look at the universe behind you, you would start to see something peculiar. The stars would begin to look slightly distorted, their light bending around the immense gravitational field of the black hole. It is a beautiful, yet ominous, sign of the extreme physics you are about to encounter. You are now steering your ship directly toward the edge of the known laws of physics, toward the event horizon. Your clock is ticking normally, your body feels normal, but you are about to cross a threshold that will separate you from the rest of the universe forever. This is the calm before the storm, the final moment of connection to everything you have ever known. You have made the decision. You fire your thrusters and cross the event horizon. What happens now? Contrary to popular belief, you do not immediately get squashed into a dot. In fact, for a little while, you might not feel anything dramatic at all. The interior of a black hole is not a hollow cave, it is a relentless flow of space and time, all rushing inward toward the center. You are now inside this flow, like a leaf caught in a waterfall. The real drama begins with a force called tidal gravity. Let us understand this with an example. The moon's gravity pulls on the Earth, creating the ocean tides. The side of Earth closer to the moon feels a slightly stronger pull than the side farther away, stretching the water. A black hole does the same thing, but with unimaginable power. As you fall in feet first, the gravity at your feet is significantly stronger than the gravity at your head. This difference in force starts to stretch you. You begin to undergo a process called spaghettification. It is a funny name for a terrifying phenomenon. Your body would be pulled and stretched into a long, thin shape, like a piece of spaghetti. This stretching is not just gentle pulling. It would be incredibly violent. Every part of your body, every molecule, would be pulled toward the center with a slightly different force. The result is that you are elongated, compressed, and torn apart. For a very large black hole, the tidal forces at the event horizon are weaker, so you might survive longer inside. For a smaller black hole, spaghettification would happen almost instantly as you crossed the horizon. It is the ultimate physical distortion, a direct and brutal consequence of the extreme warping of space. Space itself is being stretched, and you, as an object within that space, are being stretched along with it. This is the first, and for smaller black holes, the final, physical effect you would experience. Now, let us introduce a twist to our story. Imagine you are not falling into the black hole alone. You have a brave partner, let us call them Alex, who is observing you from a safe distance in their own spaceship. From the moment you start your descent, you and Alex would begin to experience time in two completely different ways. This is one of the most incredible predictions of Einstein's theory of relativity. As you fall closer to the event horizon, from Alex's perspective, something very strange happens. They see you falling slower and slower. Your movements become sluggish, as if you are moving through thick honey. The light reflecting from your spacesuit starts to stretch, causing it to shift to redder and redder colors, a phenomenon called redshift. As you approach the event horizon itself, from Alex's point of view, you would appear to freeze. You would be suspended in time, motionless, a permanent silhouette etched onto the boundary of the black hole. The light from you would become so redshifted that it would eventually fade into invisibility. To Alex, it would seem like you never actually crossed the event horizon, you just fade away over an infinite amount of time. But what about from your perspective? Inside your spaceship, your clock ticks perfectly normally. You do not feel like you are moving in slow motion. You continue your fall, and you cross the event horizon without any fanfare, without a bing or a flash of light. For you, the crossing happens at a definite moment. This is the great paradox. You experience yourself crossing the horizon and meeting your fate in a finite amount of time, while the entire universe outside watches you take an eternity to do so. From your perspective, the entire future history of the universe, the death of stars, the formation of new galaxies, would flash before your eyes in a blinding instant as you fall. You and your partner are now living in two separate timelines. You are now inside the black hole. You have passed the point of no return and are being pulled inexorably toward the center. What does this inner world look like? It is impossible to know for sure, but our theories of physics paint a bizarre and terrifying picture. The space inside a black hole is not like the space we know. It is so warped that the very idea of forward and backward loses its meaning. Think of space as a flexible rubber sheet. A planet creates a dip in that sheet. A black hole creates a pit so deep and so steep that the walls become vertical and then curve inward, forming a hole that nothing can climb out of. Inside the event horizon, all paths, every possible direction you can point your ship, lead downward toward the center. You could fire your thrusters at full power, but it would be useless. It is like trying to swim upstream in a river that is flowing faster than the speed of light. The space itself is flowing inward, carrying you with it. There are no landmarks, no stars to navigate by. The outside universe is now hidden from view, trapped behind an event horizon that surrounds you. You might see light that fell in with you, or before you, creating a ghostly, distorted glow. The central point you are falling toward is called the singularity. This is not a physical object you can see, it is a point where the warping of space and time becomes infinite. Our current laws of physics simply break down and cease to have any meaning there. It is the edge of reality itself. Your journey through this warped space is a one-way trip into the ultimate unknown, where the concepts of location and direction are fundamentally broken. You are getting closer and closer to the heart of the black hole, the singularity. This is the final destination of your journey. But what exactly is the singularity? It is the most profound mystery in modern physics. According to Einstein's theory of general relativity, the singularity is a point of infinite density. All the matter that has ever fallen into the black hole is crushed into a point with zero volume. Imagine taking the mass of 3, 4, or even a billion suns, and squeezing it into a single, mathematical point. The gravity, the curvature of spacetime, becomes infinite at this point. In reality, physicists do not believe something can truly be infinite. The singularity is a sign that Einstein's theory, as brilliant as it is incomplete. It does not work at such incredibly small scales. To understand what truly happens at the center of a black hole, we need a new theory that combines gravity, which governs the very large, with quantum mechanics, which governs the very small. This sought-after theory is called quantum gravity. Some theories suggest the singularity might not be a point, but a ring if the black hole is spinning. Others propose that it could be a dense, exotic object known as a Planck star. But for you, the astronaut, the practical result is the same. As you approach this region, the tidal forces we discussed earlier would become infinitely strong. The difference in gravity between your head and your feet would be so immense that your atoms, and even the subatomic particles you are made of, would be ripped apart. You would be reduced to your most fundamental components and added to the mass of the singularity. Your journey, and your physical existence as we understand it, would come to an end. You become a permanent part of the black hole's mysterious core. So, is that the end? You fall in, you get spaghettified, and you vanish at the singularity. While that might be the fate for any matter falling into a black hole, the story of the black hole itself is still being written, and it contains even more astonishing twists. In the 1970s, a physicist named Stephen Hawking made a revolutionary discovery: black holes are not completely black. They can, in fact, glow. This glow is now called Hawking radiation. How is this possible? According to quantum mechanics, empty space is not truly empty. It is a seething foam of virtual particles, pairs of particles and antiparticles that constantly pop into existence and then annihilate each other almost instantly. This happens everywhere, all the time. But if this particle pair creation happens right at the event horizon of a black hole, something extraordinary can occur. One particle falls into the black hole, while its partner escapes into space. The escaped particle becomes real, and it carries away a tiny amount of energy from the black hole. This process means that black holes slowly lose mass and energy over time. They evaporate. For a large black hole, this process is incredibly slow, taking many times the current age of the universe. But eventually, in the far, far future, a black hole could theoretically evaporate completely and vanish. What happens to all the information about the things that fell in? This is the black hole information paradox, one of the biggest unsolved problems in physics. Does the information about you, your atomic structure, your memories, get destroyed, which would violate quantum laws, or is it somehow encoded in the Hawking radiation? We simply do not know. Your journey into the black hole has taken us from the edge of reality to the frontiers of human knowledge. Black holes are not just cosmic vacuum cleaners, they are the ultimate laboratories where the laws of the universe are tested to their limits. They teach us about gravity, time, space, and the very fabric of reality. The truth about what happens inside may indeed blow our minds, but the pursuit of that truth is what drives science forward, pushing us to unravel the greatest mysteries of the cosmos.